Okay, so if you can try and sit down, we're a little behind schedule, so I'd like to get going, please. For those of you who were here yesterday, we were going through a lecture which we did not quite finish, so I want to start by just covering the last couple of topics on yesterday's lecture. Okay, what we were considering were some examples of orbits. We looked at one orbit where we actually modified the angular momentum while leaving the energy unchanged. In this problem here, we do the converse. So we have a satellite in a circular orbit, and it has been given an impulse, presumably firing a rocket, but the impulse is such that it leaves the angular momentum J unchanged. However, the kinetic energy is modified, describe the subsequent motion. So just before working through the actual algebra, let me just, as we did for the previous question, just consider what is happening in terms of the effective potential. So I will draw a generic effective potential which has this shape, of course. So this is the sum of the angular momentum term and the actual potential energy from gravity. So we start in a circular orbit, and as we reminded ourselves yesterday, in a circular orbit, the energy is such that you're at the bottom of the potential well. So this is energy initial. Okay, so the rule for the effective potential is such that the only allowed motion is such that you are below the total energy of the system. And if you're right at the bottom of the potential well, there's nothing below you, so you just have to sit here. So you remain at a constant radius, which is, of course, what you expect for a circular motion. But what happens here is that the angular momentum is not changed. If the angular momentum is not changed, then this curve remains the same. Remember, this curve has a term in it, which is j squared over 2mr squared. So if j doesn't change, then the curve remains the same. The only thing that changes is the energy. We will investigate how the energy changes. Presumably the energy can't go any lower. You don't get any orbit in that case, but presumably the energy is going to rise, and then you get a situation that you now can describe motion between here and here. So there's a minimum radius and a maximum radius, a perigee and an apogee. So there has been an increase of energy which has enabled us to go from a circular orbit to an elliptical orbit, while the actual form for the effective potential does not vary. Okay, so that's the qualitative discussion in terms of that. Let's just see how we would answer the question analytically. If J is not changed, then this impulse must be perpendicular to the direction of motion. Okay, it must kick it outwards. If you tried to kick it with any component tangential to the direction, then that would clearly change the angular momentum. So this is our general expression for the energy. But we start in a circular orbit, so this is so this energy simplifies greatly, of course. So this is the kinetic energy for the motion in a circular orbit. This is the gravitational term. Alpha here is just big G, big M, little m. And before going any further, of course, for the circular orbit, we can actually equate the gravitational force and the centripetal acceleration, so that actually gives us an expression for V naught squared. So for the So this is known. It's alpha over 2m, alpha over mr0. Therefore, the initial energy of the system is entirely constrained. Now, what we're told is that this impulse is going to change this kinetic energy from T, which is a half mv naught squared, to beta T naught. Okay. So in our new orbit, the energy then, if we just write this as the total kinetic energy and the gravitational potential, at the moment the impulse happens, the total kinetic energy changes from mv naught squared over 2 to beta mv naught squared over 2. So we can equate this to our general expression for the energy for the orbit afterwards. And as ever, we're interested in finding the perigee, our min, and the apogee, our max. And we do that, of course, by looking for the case where there's no radial motion, no radial velocity at that point in the orbit. So we set r dot to 0, then we get a simple expression which we can then solve. Finally, from this lecture, let us just consider the final case of the orbit, or final type of orbit, not the case where you're a circular orbit or elliptical orbit, but when you're out here, and this is of course a hyperbolic orbit, so there's not, there's only a distance of closest approach, and then that is all. So one example is a comet coming in and being deviated by the gravitational attraction of the planet. So it starts a long, long way away with a certain velocity v0. Let me just remind you of this jargon of the word impact parameter. This is useful to know. So this is its initial direction. If I draw a line parallel to that passing through the planet which is attracting it, then the impact parameter is the perpendicular distance between these two lines. And this is a useful parameter to have, of course, because this tells us what the actual angular momentum is. So the initial angular momentum is just given by m r times v, which in this case is just nothing more than mv naught h, because h, the impact parameter, is the perpendicular distance. So angular momentum is of course conserved, and we also know what the total energy is here. Now in this problem there are many things we can ask, but the only one we'll consider today is what is the distance of closest approach and what is the velocity at that moment. So what is this distance and what velocity does it have at that moment? Okay, so this is now getting repetitive. We have the same expression as ever for the energy of the orbit. We are interested at the position where r dot is equal to 0. This then gives us a quadratic equation for that distance, and this depends on J and E, and J and E we know, we've just discussed that. So we can find this solution. What is the velocity at the distance of closest approach? Well, this we get from angular momentum. We start with the angular momentum mv0h. This angular momentum is conserved when we are moving past at the distance of closest approach. Again, the velocity is perpendicular. I mean, this is a perpendicular distance, so when you take the cross product, you have a 90 degrees, so there's no angle which comes into the game. All we get is that the mass times that velocity times the distance of closest approach is equal to the angular momentum you start with, and this therefore defines the velocity. That's all I want to say about this problem today. I remind you that we did in the lecture go through this rather fun exercise of working out what phi is, an expression for phi, which is the angle through which the object is scattered. Okay. This is certainly a non-trivial calculation, but to go through this in detail, I think would distract us from the other important topics we must cover. But I believe that this working is fairly comprehensive, and it should be clear to you. But if you work through this and you have any questions, drop me an email. Right, so let us now move on to the next lecture, where we will be covering essentially moments of inertia and then Lagrangian mechanics. These are the two main topics I want to revise today. We must start with some definitions, of course, and we begin with angular velocity, which is something we've been using a lot, but this is just to pay attention to the direction of the angular velocity. So it has this is a definition, and it is a vector, and it has a direction associated to it. So if we have a motion which is if we have a linear velocity given by r dot, and we have a radius from the center of the system to the object which is moving, then r dot equals omega cross r. That defines omega. So this is a familiar expression. This is in scalar form. This is just telling you that v equals omega r. This you've been using many times, but let me remind you it is a vector, so it actually has a direction associated to it. And though the motion is in the plane here, this object is revolving in the plane, the actual vector direction we associate with omega is actually out of this plane. Okay? We can have an angular acceleration, but from all this we get we can work towards the definition of the moment of inertia, which we'll be talking about for the next 10 minutes or so. So just, this is a health and safety risk, put it there. So just to remind you how the moment of inertia enters the game, okay, let us just consider firstly a single body of mass m. So I start with J is equal to R cross P, which I can write as R cross M cross R dot, which is MR. And now I have this R dot, which is expressed in terms of omega and R. So that becomes R cross omega cross R. Okay. Now this is a triple vector product. We can use a vector identity to express this. There's two terms. So then we get J is equal to M R dot R omega minus R dot omega R. Okay, that's maths, not physics. But looking at this, because R and omega are perpendicular to each other, we realise that this must vanish, and we're left with mr squared omega. So that's for a simple, that's for a single object. So for a system of many objects, then we would sum over them, and we get J is equal to mRI squared omega, if they are all moving with the same velocity. Okay, so this is the moment of inertia, I. Okay. This is for a simple system where they all lie in this plane. But this is to remind you where this comes from. And if torque, as we defined yesterday, that is the rate of change of angular momentum, and this therefore can also be written as the moment of inertia times the angular acceleration. Okay, so moment of inertia in rotational dynamics has the same property, if you like, of mass in linear motion. Right, so a few slides we can pass over. I keep tripping over this guy. There. So this was, we were somehow considering a body there made of, if you like, discrete masses on rods. Most bodies we deal with are not like that. They are continuous bodies. And so rather than having this sum, one actually needs to go to the continuous limit where you have an integral over d squared times some volume element. So for a continuous body, we have a d squared. So this d squared is the perpendicular distance from the axis to this element dm times dm. Okay, so this is a mass element. And usually we'll be dealing with bodies which have some uniform density, so we can turn this into an integral over a volume. So this becomes d squared rho dv. Okay? So this is how we evaluate moment of inertia for a continuous body. So we have an axis through that body. We work out the perpendicular distance from that axis to some volume element, and we perform this integral. Okay. This, I think we should just remind you, this is a very busy slide. The only thing I want you to take from this is that for any object, because you can put 3 orthogonal axes through that object, so there are 3 axes, so one can calculate 3 moments of inertia with respect to those axes, and you should choose these axes such that this very complicated entity here just reduces to a very, very simple matrix with 3 numbers. This will almost certainly be what you are facing most of the time in any prelims question. The axes will be chosen, so you're dealing with the moments of the actual axes of symmetry, and then the system becomes very simple. You have 3 discrete moments of inertia. Let me just skip over that slide for a moment and move to this slide, just to, having reminded you of this, let's just see this in action for a very, very simple calculation. So this is working out the moment of inertia for some rectangular plane. So we can define, well, let us define axes through the axes of symmetry. So this is x, this is y. There's another axis z pointing towards us. Let us say that this is of length a, and this is of length b. So if we want to work out Ix, so the moment of inertia with respect to the x-axis, we just need to take an element there, okay, and we need to, so this is an element, and this will be a distance y away from that axis. So Ix then will be given by just following this recipe. This is a perpendicular distance, something which we should have stressed. So we have the integral over y squared dm, because y is the perpendicular distance from the x-axis to this element, which becomes, so this integral then we replace the dm by an area integral. We're dealing with a two-dimensional object, so rather than volume we deal with area. So y squared rho, this is the density, dx dy, okay? This now should be jogging your memory. Okay, so to enable us to not lose too much time, having set the integral up, I think we can just follow this on the board. The y squared becomes a y to the cubed over 3. You put in these limits, and you also must integrate over x. So you end up with this rho ab b squared over 12. Rho is something that we actually somehow introduced to be able to do the problem. Rho is, because it's the density of this two-dimensional object, it's just the mass divided by the area of that object. So having got the result in terms of rho, we can then put the mass back in using this definition. We have mb squared over 12. Of course, if you were to do the exercise about the other axis, you would have ma squared over 12. There's a third axis in the game, as I mentioned. There's the z-axis coming towards us. You could calculate the moment of inertia from this z-axis in a similar manner, but let us actually come back to that when we look at the parallel and perpendicular axis theorems, because this is a much quicker way to get at that result. The slide I skipped over, this is something to dwell on, but let us maybe not absorb these lines of definition, but just cut to the chase and go to the bottom line. If we're dealing with rotational motion, there'll be some kinetic energy associated with that rotational motion. And that kinetic energy can be written as a half I omega squared, I being the moment of inertia, of course. So this is the moment of inertia about the axis of rotation where the motion is happening. This expression, of course, is very, very analogous to that which one gets just from the linear motion. Okay, I think it comes next. Yes, so I alluded to these theorems that if you calculated moment of inertia about one axis, there are some handy theorems which allow you to then get at the moment of inertia from about another axis. So there are two of these theorems. The first is the parallel axis theorem. So we have some body and say that we have an axis going through the center of mass of that body. And we know what that moment of inertia is. It's just given by this sum. Now let us imagine we put another axis through the body which is parallel to that one. Okay, so the question is, what is the moment of inertia about this? So it could be that the integral here is more awkward to do. What is very nice is that this theorem exists, which gives us a very simple relation between the two. Okay, so just to repeat what's written on that slide, so about the parallel axis, we have that I is given by the integral over r prime squared dm, where r primed is this perpendicular distance from the axis going through O, but we have r primed is given by d plus r in vector terms, where d is the vector which takes us from the axis going through O to the centre of mass axis. And so r squared is given by d squared plus 2d dot r plus r squared, and hence I, the moment of inertia through the axis O, is given by d squared dm, so I'm just writing these three terms in separate integrals, plus 2d dot r dm. That d is a constant, so I can take it out of the integral, plus r squared dm. So we look at this for a moment. We say, well, the first term, this is easy because d squared, as I say, d is a constant, so this is just an integral over dm, so this is nothing more than md squared. Okay. This term here, integral of r squared dm, that's nothing more than the actual moment of inertia through the centre of mass. This is just ICM. And what's coming is that this term there, that term is 0. Why is it 0? It's because this is just, so this is evaluated, this is the mass elements with their distance from the centre of mass. So by the definition of the centre of mass, if you make this integration, everything to one side will cancel with everything to the other side. So that becomes 0. So this is definition of centre of mass. And hence, I is given by ICM plus md squared. Okay. So if we have the moment of inertia of centre of mass, we go to another axis a distance d away, then the moment of inertia about that other axis is given by that expression. We have a perpendicular axis theorem. This has a more restricted applicability because strictly this only works for two-dimensional objects, a rigid object that lies entirely within a plane. So we can stretch the definition to thin objects. But anyway, let us say we have these three axes, x, y, and z. So this, for instance, this object could be like the two-dimensional rectangular sheet we were talking of. This is the definition of the moment of inertia about the z-axis, the axis pointing out of the plane. So this involves d squared dm, so this is d. But d, of course, is nothing more than the square root of x squared plus y squared. So we can make this substitution, and this immediately becomes, this we associate with I, y, the moment of inertia about the y-axis. This is the moment of inertia about the x-axis. So you end up with this very simple and elegant relation that Iz equals Ix plus Iy. Okay. Let's put these things into operation by considering the compound pendulum. So the compound pendulum, rather than being a string with a bob on the end, this is instead, it's like a ruler. It's a rectangular rod of uniform mass with length A and width B. Okay, so it has a centre of mass which is clearly in the middle of the rod, but we pivot it and swing it about a point which is a distance L away. Okay, So what is obvious is that to make progress in trying to write down an equation of motion, we're going to need to know the moment of inertia about an axis going through O. Okay, so what is this? Well, firstly, we need to do this in two steps. Firstly, we need to know what the moment of inertia is through the centre of mass. So if you think about it, this rod is just like this plane we worked out a few moments ago, what the moment of inertia is for about an axis, an x-axis and a y-axis for such an object. We didn't work out what the moment of inertia is about the z-axis, the axis coming outwards. But here we can use the perpendicular axis theorem. So this gives us that the moment of inertia about the centre of mass, which is Iz, is just Ix plus Iy. These are the two things and which we just worked out, and we end up there with nothing more than ma squared plus b squared over 12. Okay, so that's great, but this just tells us the moment of inertia about this axis. We are swinging it about this point. Okay, so we now we need to know what the moment of inertia is about point O, and to do this we realise that this axis is a parallel axis to this, and therefore we use the parallel axis theorem. Okay, so this tells us that I subscript O, as I have it on the board, is just ICM, which we worked out, times the mass of the object times the distance between the axes squared, which is just L squared. Okay. Okay, so this I don't write out the expression, but it's just this plus ml squared. Okay, so we have the moment of inertia about the point we're interested in. Why do we want this? Well, we know that J is given by I omega this I being the I we've just evaluated, and the torque tau is just the rate of change of J, so that is just given by I naught omega dot which I've expressed here. I've written because I want to use this z-axis, I can write omega dot as a theta dot or theta double dot, in fact, because omega is theta dot. So omega dot, the acceleration is theta double dot times k, which is this axis. Okay, so that is an expression for the torque, and I equate this with what we actually can evaluate the torque to be. See that the torque is nothing more than this distance here multiplied by the force of gravity resolved in this direction, which is nothing more than minus mgl sine theta. Okay, the minus sign because gravity is seeking to actually decrease theta. Okay, so we end up with this expression on the bottom. which is now on the top. Here I put in the actual expression we calculated for the moment of inertia, and we make a small angle approximation because theta is a small angle, and we can write sine theta as theta. This, of course, gives us simple harmonic motion. From this, we can calculate the period, should we wish. Okay. The final example, well, discussion of angular momentum is this ball rolling down the slope. So this somehow brings many things together. What we wish to do in this case is to work out, if we start it at the top of a slope of height h, what velocity does it reach at the bottom? So in general, when it's some distance down the slope, it will have some potential energy, and it will have kinetic energy coming both from its linear motion and from its rotational motion. Okay, so as we said earlier, we can write kinetic energy decomposed into the rotational and the linear terms. Okay. The only awkward aspect of doing this is that we seem to have two variables in the game, omega and v. We then can say, well, if the ball does not slip, this means that as it rotates, then the ball will move a certain distance along the slope, so that there's a one-to-one correspondence between how much it rotates and the distance it covers. In other words, that omega is equal to v over r. So this is a constraint, which we'll come back to shortly, relating the linear velocity with the angular velocity. So if we impose this constraint, we can then combine these two kinetic energy terms into a single term here, and therefore we say, well, the kinetic energy at the bottom of the slope is the potential energy we started with, and from this we can work out the velocity. This making use of the moment of inertia for a solid sphere. The expression we end up with, we can then reapply not just for a sphere, but for example for a cylinder. This has a different moment of inertia, and therefore the cylinder will reach the bottom of this slope with a different velocity. Turns out to be this result here, which you see is actually less than that. So interestingly, the sphere would roll down the slope more rapidly than a cylinder. Okay, so finally let's move to the Lagrangian mechanics. Something hard to do justice to in 10 minutes or so, but we will do it. This is if we stick to practicalities, which I think we must do this close to the exam, what is important thing to remember is the Euler-Lagrange equation. Okay. What we have on this slide is a justification of this for a simple system. But let us, for the exam, we'll be interested in its application. You remember that we actually looked at deriving this equation in various ways, in particular using the calculus of variations. That is, I think I'm right in saying, off syllabus. What's more important is that you know what this equation is and you know how to apply it. So this equation relates what we call, it relates variables which I've given the subscript k. There could be n of these variables. Typically you'll be dealing with problems with 1, 2 or 3. And so this relates the variable and the variable's time derivative. So e.g., so you could have that q1 is x and q1 dot is therefore x dot. And you will have, for each of these so-called coordinate variables, you will have a Euler-Lagrange equation you can solve. And solving that equation will give you the equations of motion. You get the equations of motion without having to think about forces, and that is the beauty of Lagrangian mechanics. I will remind you of how it works with an example, but here are some definitions. This is jargon, but jargon that it's, I think you should know, because questions can be phrased in terms of these terms. So one talks about the generalized coordinate. So this is this set of coordinates QK here, right? That specifies the system configuration. So QK may be a geometrical parameter, so I've written here x, or it could be a set of angles. One talks about degrees of freedom also, so that's the number of independent coordinates that is sufficient to describe the configuration of the system uniquely. Constraints. Constraints are, things about this system, things imposed on this system, such that which either relates the coordinate variables, the generalized coordinates, or it just restricts the coordinates and does not allow them to move freely in 3 dimensions. So some of these constraints you will just implicitly see and make use of. For instance, if you have a ball rolling on a table, that ball can only move in 2 dimensions. The table is constraining it and not allowing it to move vertically. Conjugate momentum, okay, so conjugate momentum, that's important, worth writing down. That is PK equals dl by dqk dot, okay? So that is something which it can be nothing more than just a normal momentum, but if we're dealing with an angular variable, for example, it will turn out to be an angular momentum. But it means that in this system we can relate a momentum to one of the generalized coordinates. Okay. So what is elegant is that if you make this definition, you can then actually rewrite this equation in these terms, making use of the generalized momentum. Moreover, if you write down the Lagrangian, and the Lagrangian has no dependence on QK, so say the Lagrangian has no dependence on x. The Lagrangian may have a dependence on x dot, the velocity, but say it has no dependence on x. In this case, then, from looking at the Euler-Lagrange equation expressed in these terms, the right-hand side will, of course, be 0, and therefore the rate of change of the generalized momentum, which would be the x component of the momentum, will be 0. So that tells you that that component of the momentum is conserved. So the jargon from this is that if the Lagrangian has no explicit dependence on qx, then that coordinate is cyclic or ignorable. And the momentum conjugate to a cyclic coordinate is a constant of motion. So this is one of the beautiful properties of Lagrangian and indeed Hamiltonian mechanics, that you can just actually look at the Lagrangian and you can see immediately what quantities should be conserved. Okay, let's look at just one example, which is again the pendulum. This time this is a simple good old-fashioned pendulum, so it's just a bob on the end of a string of length L. The Lagrangian, of course, we didn't say this, the Lagrangian is defined, of course, as T minus U. U is the potential energy. Okay, so in this case we write, we know what the velocity is, we can write that as L theta dot. It will turn out in this game the only generalized coordinate we have is theta. Okay, So the kinetic energy of this object at the end of the bob at the end will be a half ml squared theta dot squared. We have some potential energy due to its height. Okay, so we write that as minus mgl cosine theta. Okay, so this is defined such that it vanishes to 0 when theta is at 90 degrees. So therefore, the total Lagrangian is just summing these up. A very, very simple Lagrangian depending on just a single variable, theta, and its derivative. So this is a 1 degree of freedom. We apply the Euler-Lagrange equations, and Bob's your uncle, you end up with this, which we immediately recognize as being the equation of motion. So applying the Euler-Lagrange equation to the Lagrangian gives us the equation of motion. Now the thing I want to now talk a little bit more about is including constraints. So there was a constraint in this problem which passed us by, which is that this distance here was constrained to be L. So we made the pendulum a distance, a length L, and that restricted the motion of this object. So that was fine, and we got the right answer. But in solving this problem, we learned what we didn't find about was the actual forces which are existing, for instance, the tension in this string. This is interesting information, and we can get that information from the problem. And this is where constraints come in. So the constraint we had here is that the pendulum has length, I say R, that's a typo, it should be length L. This we actually put in when we wrote down the Lagrangian, that's fine. But to get more information out, we can actually leave the pendulum as just saying it has length R, and I'll show this, but constrain, add an extra term to the Lagrangian to constrain this length to be L. Okay, this will, if you don't remember this will be very apparent on the next slide, so hang on in there. So this is done, it can be done in a couple of ways, but the way I want to remind you is the use of Lagrange multipliers. So we add an extra term which encodes this constraint, and this has a factor at the front which we call lambda. And when we solve the problem, we need to add an additional Euler-Lagrange equation for this constraint lambda. And doing this, we should end up with the same result we had before, but we can get added insight because this is the payoff at the bottom here. That if we find out what this lambda is, and we take the derivative of the constraint equation with respect to a given coordinate variable, this will give us a force which is imposing the constraint. This may look very mysterious, so let us actually see it in action for this pendulum. Okay. So what we will do here is now rewrite this Lagrangian, but we won't say that the pendulum has length L, we will leave it as R, okay? So we now got two variables in the game, R and theta, but we have this constraint that in fact we know that the pendulum should have length L. So we have this constraint that R minus L is equal to 0. And this is a constraint, and this is actually called a holonomic constraint. You can have constraints which are not holonomic, but believe me, you won't get one of those on your prelims paper. So the first three terms of here should be no surprise. So now we're allowing so this is all clear. So we're allowing for the possibility that this length R is not is a variable. Hence we get these three terms. But then we add this final term, which is the holonomic constraint. The left-hand side of this equation, but multiplied by this Lagrange multiplier, lambda. Okay. So now we solved the Euler-Lagrange equations. So we must do it for r and theta, but also lambda. Okay. So this is what you get if you do that. The final one with lambda, that's just given us r minus L. So that's just actually recovered constraint. So once you have this, you can actually then put back in that r is a constant and is equal to L, and that, for instance, it makes the left-hand side of this disappear, and you recover the same results as before. But you also get a result for lambda, lambda being minus mg cosine theta minus mr squared theta dot squared. And as I said on the previous slide, lambda multiplied by the derivative of this constraint equation with respect to r gives you just lambda, because this derivative is trivial. And this we interpret as a force associated with the r direction. And this force is the tension. Okay, so the constraint has enabled us to get a tension in the game. It's told us about one of the forces which is actually constraining the system. One can also evaluate the derivative with respect to theta, and you'll get 0, because there's no, this constraint is doing nothing in the theta direction. Right, that's somehow important. The last few slides I can move over more quickly, I think, which is we have to do given the limited of time. So this was the Lagrangian. You can write in various coordinate systems. So you should be happy with expressing the kinetic energy in terms of cylindrical or spherical coordinates. And this was a problem I remind you of for the lecture. So this is a bead on a hoop. So here it's appropriate to use spherical coordinates. And you see that the bead is constrained. I mean, there's constraints in this system, but they're all implicit. The only way the bead can move is in phi, or theta as I've written it, I apologize. So one writes down the Lagrangian, and it turns out that there's only a single generalized coordinate, theta, because the motion in this direction is given by omega, that's the velocity, that is fixed. And this distance r is fixed. There's constraints which are fixing this. Okay. Then, so if you apply the Euler-Lagrange equation for this single variable theta, you get this equation of motion here. Okay. If you consider the special case when it is not spinning around and omega is 0, then this immediately just reduces to something which just looks like simple harmonic motion for a pendulum, so that seems to make sense. Finally, very finally, this Hamiltonian mechanics is a vast subject, but it just appears right at the end of the course. If you have a question on this, I don't know, I'm not the examiner, but it's very, very likely if you do have a question, it will just be a short question in the A section. But the Hamiltonian is re-expressing Lagrangian mechanics, but in terms of the conjugate momentum. So this is the conjugate momentum, and the Hamiltonian is defined as being the sum over this conjugate momentum multiplied by the, if you like, the velocity associated with that coordinate. Sum over these minus the Lagrangian. If I just move to these lines here, what does this strange object, the Hamiltonian, represent? Well, if you just take a single one object has a kinetic energy here, this in Cartesians, if you therefore write down what the Lagrangian is, if you perform this sum for this object, so so for instance the first term is when k is x, and you have so the momentum is mx dot, and then multiplied by x dot, ditto, ditto, ditto. That minus the Lagrangian will give you something which you can immediately see is actually the total energy of the system. So in many cases, the Hamiltonian is nothing more than the total energy of the system. But it is not always so. This is another important relation we showed, that actually the total time derivative of the Hamiltonian is equal to the minus the partial derivative of the Lagrangian with respect to time. This means that if the Lagrangian has no explicit dependence on t, so if you write down the Lagrangian and you see no t anywhere there, then the right-hand side will be 0, and hence h must be conserved. It must be a constant of the motion. And because in many cases h is nothing more than the total energy of the system, then we see that this is a statement of the conservation of